Hello everyone, and thank you for checking out the complete beginners course in Spatial Data Science and Applications. That's Understanding Spatial Data Science Part 1. In Part 1 of this video, we will concentrate on understanding geospatial data science. To give you the concept of geospatial science, we will first of all look at related disciplines such as natural sciences, data science, and then discuss the definition of geospatial science and its unique aspects. Discuss the differences and commonalities between data science and spatial data science. For a better understanding, examples of problems in geospatial science are also presented. Does anyone know what science is? What is science? I present two definitions here, one from Wikipedia and the other one from Webster. According to Wikipedia, science is a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. Science is a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. This is the definition given by Wikipedia. Now let's look at the definition given by Webster. According to Webster, science is knowledge or a system of knowledge covering general truths or the operation of general laws, especially as obtained and tested through scientific method. What is the underlying differences between the two definitions given above? The core differences between the two definitions given above. One is focusing on activity or method, and the other one is more on subject. As a subject, science is a set of human knowledge on general truths. As an activity or a method, science is used in making reproducible observations and experiments based on careful measurements of the natural world. Traditionally, science method pursued finding causal relationship. In other words, it was used to answer why. Why is this happening? Why is this happening? For that, a hypothesis was set and tested with the experiment, which is precisely designed, particularly removing any biases. Sometimes other approaches could be used. No matter what, focus on scientific method was always on establishing causal relationships. Now, let's move to data science. Data science is the spotlight recently in the era of big data. Data science is growing with tremendous opportunities. A predicted 2.7 million open jobs in data analysis and data science related careers in 2020, source IBM. 29% growth in employer demand for both data scientists and data engineers by 2020. What is data science then? What is data science then? How do you define data science? how do you define data science? I'm going to give two definitions of data science. That's, again, one from Wikipedia and the other one from Cambridge Dictionary. According to Wikipedia, data science is an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from noisy structured and unstructured data, and apply knowledge and actionable insights from data across a broad range of application domains. Data science is related to data mining, machine learning, and big data. According to Cambridge Dictionary, data science is the use of scientific methods to obtain useful information from computer data, especially large amounts of data. In the definition of the data science, there are three noticeable words. One is interdisciplinary, which means that data science requires understanding of multiple disciplines and the combination. Two, insight replaces truth in the definition of science, which means that data science is not pursuing general truths or general laws. Data replaces hypothesis and experiment, which means that data analysis is the major tool to find knowledge and insights. The term data science has been traced back to 1960, when Peter Neal proposed it as an alternative name for computer science. However, the definition was still in flux after the 1985 lecture in Chinese Academy of Sciences in Beijing in 1997. C.F. Jeff Wu again suggested that statistics should be renamed data science. He reasoned that a new name will help statistics shed inaccurate stereotypes, such as being synonymous with accounting or limited to describing data. In 1996, the International Federation of Classification Societies became the first conference to specifically feature data science as a topic. Then in 1998, Hayashi Shikyo argued for data science as a new interdisciplinary concept with three aspects: data design, collection, and analysis. So the three aspects are the data design, collection, and analysis. All in all, the focus of data science is placed on correlation. The focus of data science is placed on correlation based on the data analysis rather than causality. Data science generally does not try to answer why or cause and effect. So it is clear data science does not answer the question why or cause and effect. To become a data scientist, he or she needs to have expertise in a variety of disciplines, such as database management, big data systems, such as Hadoop, should be understood for data handling and management, such as machine learning, data mining, data visualization, and application domain knowledge should be adhered to. Experience of data visualization is a big plus for delivering of results and visual analysis. Spatial data science is similar to data science in definition, but there's a major difference that spatial data science equally focuses on both causality and correlation. In other words, spatial data science pursues answers to the question why, and also a simple pattern of spatial phenomena. Spatial data science is also multidisciplinary, so that spatial data handling and management are important disciplines. With a given diagram, the relationship is also illustrated. Spatial data science has overlapped area with data science. At the same time, it has different aspects from data science, which is named as spatial science. We could find quite a few fields related to spatial data science, seeking knowledge of spatial phenomena such as urban traffic problems, healthcare issues, for example, regional prevalence of specific diseases, politics, business intelligence, city operation, hydrology, disaster vulnerability, emergency service, and many others. Let's take a look at real-world problem of spatial data science. What is the revenue estimation of a new restaurant located at Accra, Ghana? Or where is the optimal location of a new restaurant in Accra, Ghana? How can you get the answers to the questions? There are two approaches to this. One is causality approach, and the other one is data mining approach. Causality approach based on spatial science investigates supply side and demand side, location and capacity with nearby competing stores are ascertained. Spatial distribution of potential customers are carefully mapped, and service accessibility models such as gravity model or two-step floating catchment analysis are applied. Finally, customer shares are estimated and eventually get an revenue estimation at a given location. On the other hand, data mining approach is to find the existing restaurants which has a similar pattern of new restaurants and then use the revenue of the existing restaurant as the estimation, or build a regression model of which target variables is revenue and input variables are characteristics of store and its location, and then use the model for revenue estimation. Which approach do you think is more appropriate than the other? In general, data mining approach works very well in case of small retail shops such as coffee shop. On the other hand, causality approach works better for larger stores such as grocery store, department store, and so on. The next problem is how long will it take to leave KNUSC for Amstead by Uber at 6 o'clock p.m. Monday? There are two approaches in solving this spatial problem. One is the causality approach and the other one is data mining approach. Causality approach takes steps such as trip generation to build origin generation table, model split about decision making of transportation type, trip assignment to routes, and then get their travel time estimation. Data mining approach uses historical data sets of Uber trajectory, then find a similar trajectory which covers the origin KNUSC and then destination Amstead, and the similar condition parameters such as 6 o'clock p.m. Monday, weather conditions, and occurrence of any spatial events. Based on the trajectory of pattern mining and matching, the travel time can be estimated as well. The next question is, what is the air pollution level at KNUC at exactly 10 o'clock p.m. on Monday morning? There are two approaches in answering this question. One is the causality approach and the other one is data mining approach. The causality approach is to combine inventory of pollutant emission and weather condition into computational fluid dynamics and estimate air pollution level at given location and time. Data mining approach will train a machine learning algorithms which takes in air pollution data and produce air pollution map of a given condition. The last example is hydrological question. Where will be flooded in the city of Kumasi at 1 inch per 1 hour for 6 hours? Causality and data mining approach will be applied. We can use either conventional hydrological processes with spatial data, such as digital elevation model, which is a causality approach, or a heuristics data mining approach with pattern matching. There are four main disciplines of spatial data science. That's geographic information system, spatial database management system, spatial big data systems, and spatial data analytics. These topics will be discussed later. Alright, this is the end of the first lecture. Hopefully you enjoy it and see you in the next lecture. Kindly subscribe to my channel to keep pushing me. Welcome back, ladies and gentlemen. In the previous video, we talked about the introduction to spatial science and its application. Thus, we define science, data science, and spatial data science, as well as commonalities between them. A great comparison was also made concerning data science and spatial data science. Finally, spatial data science problems were also proposed, as well as ways of solving them. If you've not watched the previous video on Introduction to Spatial Data Science and Application, kindly look at the video description of this video and watch it. If you have not also subscribed to my channel and you like my work, you like my video, kindly subscribe, like, share, and comment. Now let's move to today's lecture. In this lecture, we will discuss unique aspect of spatial data science. Why is spatial data so important? Looking at business perspectives. First, I would like to give you a brief overview of the presentation outline. The presentation outline encompasses the following. I'm going to give you a brief account of my friend's personal experience in an IP firm. And then I'll move to 3 commonalities of IP companies. Then we'll also talk about 5 reasons why IP companies have in-house maps. And later I will now give you a summary of the whole presentation. Let's talk briefly about my friend's experience in an IP company. Balunga is my friend who was employed by Joe System firm in 2002 as a GIS technician. On one fateful day, her boss moved to her office and asked her why Google acquired the KEYHOLE, she could not give an answer to her boss at that point in time. Balunga went home and brainstormed on the question of why Google acquired the KEYHOLE. Please let me kindly give you a brief background on the KEYHOLE. KEYHOLE is a company specializing in web-based software that allows people to view satellite images from around the globe. KEYHOLE, founded in 2001, offers software that lets internet users view geographic images collected from satellites and airplanes. The technology relies on multi-terabyte database of mapping information. The software gives users the ability to zoom in from space level. In some cases, it can zoom in all the way to a street level. Call it street view. The company does not have high resolution imagery for the entire globe, but its website offers a list of cities that are available for more detailed viewing. The company has focused most on covering large metropolitan areas in the United States and is working to expand its coverage. Back to my earlier question again. Why did Google invest its money in acquiring KEYHOLE? In the business world, a company never invests even a single dime without a cause. What is the objective of the investment? That is my question. At that time, Google only provided a small search window and just expanded its service to email in 2004. Of course, no mapping service. The answer was so obvious. What other purpose could Google have for the acquisition of KEYHOLE except for offering a map service to make money? The KEYHOLE acquisition was for business purposes. According to Google, the KEYHOLE firm has a market value of nearly $4 billion as of the year 2019. The company's market value currently will be more than $4 billion. Now, let's move to a new question. What do you think Amazon, Nokia, Apple, Google, and Microsoft have in common? I think the company has 4 things in common. What are they? First of all, they are or used to be world #1 company in the sector of IT industry. Secondly, they attempted to develop or they have developed their own operating systems. iOS for Apple, Android for Google, Windows for Microsoft, Symbian for Nokia, and Fire for Amazon. Third, they all have their map products in-house. Now you can see 3D maps of downtown of Accra, Ghana, offered by the company. Finally, they provide products and services. You all know that these major IT companies provide products and services to their clients. Now, it is natural to raise another question. Why do the major IT companies have maps in-house? Why? The first and simple reason is that spatial data is excellent content. Just think about how often you access map service through your smartphone. These days, everyone uses maps on their smartphones. However, it will not be enough to justify all the frenzy around in-house map production of major IT companies. If it is just content, outsourcing could be simple and viable solution, no matter how good it might be. The second reason is the spatialization of information. This concept tells that most of the information has a location so that it can be managed with location. In other words, information can be organized on top of a map. If this could be applied, a search engine can present different results to different users at different locations. Now more business transactions are made on mobile devices than on traditional desktop computers. In this situation, location-based advertisement designed for mobile devices is the game's name. More seriously, it's a matter of survival for any company in online advertisement, including Google. The fourth reason is the interface between humans and robots. The figure is showing drone delivery. A map is a basis to allow the robot to recognize its origin and destination for either delivery. Through a map as an interface, human intention can be understood and mission can be completed by a robot. There was quite a big case that supports my argument. 3 German motor companies, Audi, BMW, and Mercedes, together acquired Nokia Here Map in 2015. Why? Mainly to take an initiative in the autonomous vehicle market. Their plan seems to make maps play a central role in presenting high-definition spatial information, as well as sharing spatial context awareness with other vehicles. This trend was even accelerated recently. December 2016, a Chinese consortium, including Tencent, acquired a 10% of stake in Here Maps. And a week later, in the year 2017, Intel also acquired 15% of Here Maps. Microsoft also presented its plan to work with Here Maps for the IoT, that's Internet of Things strategy. Last but not the least, the map is a platform for almost everything, including big data. Human is a creative living on Earth, and almost all activities are intrinsically spatial. It is said that there are 3 major sources of major big data. These are people, machines, and organizations. Any big data can be represented on a table map. They are called spatial big data, which is one of the main topics in this course. Now we can summarize the value map with the sentence next to me. Map or spatial is a platform and interface on which human, space, advertisement, hardware, software, content, service, and future robots, and IoT, that's Internet of Things, can be integrated all together. This is the true value of map, the core infrastructure of future IT industry. Now back to the original question. Why is spatial so important? Spatial is a critical issue, a matter of survival for big name IT companies. Spatial will make a sustainable impact on the way of our living. Spatial is a platform and an interface for almost everything related to human beings. Conclusion and recap. This is the end of the lecture in which we discuss why spatial is special from business perspective. In the next lecture, we will discuss the same question from a technical perspective. If you've not subscribed to my channel, consider subscribe to my channel to keep me going. Hope you are all enjoying this lecture and see you next. Welcome back, ladies and gentlemen. In the previous lecture, we tried to figure out the answers to the question, why is spatial data so important, looking at business perspectives. In this lecture, we will discuss the answers to why spatial data is so important, looking from technical perspective. I will particularly focus on spatial data management and processing. The next slide will present the outline of the presentation. I will give you the answer from 4 different categories. Spatial data in database management system, which is about technical difficulties in storing spatial data in database management system. Topology of spatial data, which is about tight relationship among spatial objects, point, line, polygons. Spatial data indexing and related problems, and difficulties in applying multi-dimensional data indexing. Spatial big data processing, thus problems and difficulties in applying data parallelism to spatial data. Spatial information is expressed in terms of point, line, polygon, or images. Point is a geometric element defined by a pair of x and y coordinates. Line is a shape defined by a connected series of unique xy coordinates pairs. A line may be straight or curved. Polygon is closed-shaped, defined by a connected sequence of xy coordinates pairs. Where the first and last coordinates pair are the same, all other pairs are unique. Points, lines, and polygons datasets are not conventional data types such as numbers, date, and text string, which means that conventional relational data management systems cannot accommodate such datasets in the table. In fact, we can break down spatial data, in the case a polygon, and save it into tables as in conventional relational database management system, as shown in the figure. Topology deals with spatial properties that do not change under specific transformations. In geodatabases, the arrangement that constrains how point, line, and polygon features share geometry is called topology. For example, street centerlines and census blocks share geometry, and adjacent soil polygons share geometry. Topology defines and enforces data integrity rules. For example, there should be no gaps between polygons. It supports topological relationship queries and navigation. For example, navigating feature adjacency or connectivity. Supports sophisticated editing tools and allows feature construction from unstructured geometry. For example, constructing polygons from lines. Topological relationships are built from simple elements into more complex elements. Nodes define line segments. Line segments connect to define lines. Lines define polygons. A simple but naive representation of area features will be to list for each polygon the lines that describes its boundary. This is called a polygon by polygon representation. Each line in the list will be a sequence that starts with a node and ends with one. The reason why this is not a good representation is called data redundancy. This means that shared boundaries between polygons are stored double. Another disadvantage of such a polygon by polygon representation is that if we want to identify the polygons that border each other, this is difficult search analysis. When storing the second boundary, some line segments are duplicated. The boundary model or topological data model is an improved representation of polygon by polygon model. It stores parts of a polygon's boundary as separate line segments. Why is topology useful? Ensuring geometric correctness of data, detecting and correcting digitizing errors, carrying out some types of spatial analysis, selections, network analysis, find all light poles that are inside partial, find all the plots adjacent to a river, network analysis. Now let's take a look at issues of spatial data indexing. As B-tree is standard indexing method in conventional relational database management, R-tree, which is multi-dimensional extension of B-tree, considered as a de facto standard in spatial database management system. The figure contains quite a few spatial objects distributed in 2D space. The key idea of R-tree is to group nearby spatial objects and to represent them with minimum bounding rectangle, also known as MBR. In the next level of the tree, the figure illustrates how to group the given spatial object with MBR. The next figure illustrates the R-tree structure of the given spatial objects and MBRs. Leave nodes in the bottom store spatial objects. As with the other tree indexing, the searching algorithm is quite simple to check a search rectangle similar to B-tree. One major problem is that a very large overhead is required building R-tree. Can we apply R-tree to spatial big data? The answer is rather negative due to the high computation overhead. Now, let's extend our discussion to spatial big data computing based on understanding the nature of spatial data management. MapReduce has been the most popular programming framework for big data processing with a parallel and distributed algorithm on a cluster. Hadoop is still the most widely MapReduce framework using Hadoop distributed file system, also known as HDFS. Although Spark is gaining more and more popularity recently. The figure in the slide is a very simple conceptual diagram of Hadoop system for big data processing. As the name implies, MapReduce jobs are principally composed of two steps: the map step and the reduce step. The map step, which takes a set of data and converts it into another set of data, where individual elements are broken down into tuples of key and value pairs. The reduce step takes the output from map as input and combines those data tuples into smaller set of tuples, you can see a problem already. MapReduce uses only single key, which is one-dimensional, not two-dimensional key. Spatial relationship could hardly be considered and is not appropriate for spatial data processing. Overall, MapReduce is ideally suited for simple parallel computation on large size of data. But if computation that each node depends on data that resides on other nodes, the performance will be rapidly decreased. It is cut off for jobs such as web crawling, log analysis of typical big data processing, where dealing with velocity, volume, variety is more important than guaranteeing 100% data integrity and completeness. Now, my question is, how appropriate do you think is MapReduce? Maybe when dealing with spatial big data. In reality, a certain application of MapReduce to spatial big data problems came up with disastrous performance. Why? Because of the nature of spatial data. Strong spatial autocorrelation, interrelated topology, interdependency of spatial data components, which are hardly supported by conventional MapReduce framework. Then what will be alternative solutions? Well, alternative solutions are problem dependent. Sometimes even conventional Hadoop works beautifully for spatial big data problem which it deals with. For example, independent point events for noise removal, perhaps, and another value proposition of this course will be to make learners understand potential as well as the limitations of big data computing for spatial data. In this lecture, we have discussed the answer to the question, why is spatial data so important in terms of spatial data management and processing. Alright, this is the end of the lecture. Hopefully you enjoy it. And if you've not subscribed to my channel, kindly subscribe, like, share to push me to go forward. Welcome back, ladies and gentlemen. In the previous lecture, we attempted to answer the question, why is spatial data so important, looking at technical perspective. In this lecture, we will discuss the answers to the same question. Why is spatial data so important from the perspective of spatial data characteristics and analytics? The next slide shows the outline of the presentation. The following will be discussed. The first law of geography, which is about spatial autocorrelation issue, coordinate system issues on transformation between 3D and 2D space, uncertainty, which is about the fact that spatial data is basically probabilistic, modifiable area unit problem. Different aggregations will make different outcomes in spatial analysis. Dr. Tabula in 1970 stated the first law of geography. Everything is related to everything else, but near things are more related than distant things. This is a fundamental concept of spatial autocorrelation, applicable to all spatial variables. An example is sea surface temperature, for which one might expect a high degree of correlation between measurements taken close together. In the case of elevations, a simplistic interpolation function takes the elevation value of nearest stored location and assigns this to the location that is not stored. Smarter interpolation functions involving more than a single stored value should be preferred. Spatial autocorrelation can be defined as the measure of the degree to which one's object is similar to other nearby objects, so that positive spatial relationship or spatial autocorrelation is assumed reasonable for spatial phenomena. On the contrary, in most statistical analysis, independence of data is generally assumed, so the strong presence of spatial autocorrelations makes spatial analysis complicated. The next issue is coordinate system. There are mainly two ways of representing locations with coordinates: geographic or 2D Cartesian. Geographic is based on 3D. Longitude, lambda, latitude or phi, and ellipsoidal height with a small h. On the other hand, 2D Cartesian is simply x and y. When you apply any analytics to your spatial data, you have to check the coordinate system in the very first step. Think about a given problem. If you have spatial data with geographic coordinates and the sample distance computation is not an easy task at all. Moreover, there are thousands and thousands different map projections and coordinate systems. So clear understanding of coordinate system is required for advanced spatial data management and analytics. Another important aspect of spatial data is uncertainty. Spatial data is basically measurement and intrinsically prone to error. As a result, any analysis result of spatial data is stochastic. In other words, probabilistic. Stochastic having a random probability distribution or pattern that may be analyzed statistically but may not be predicted precisely. Let's see the example on the slide. When you see $1,000 on your bank account, it's literally $1,000, and in this case, deterministic. On the other hand, when you have a human trajectory collected by GPS unit, the location XY inevitably has uncertainty. As a result, when you conduct any further analysis with the trajectory, the result is probabilistic. So we have to understand the nature of spatial data and to get used to living with uncertainty in spatial analysis. In this lecture, we have discussed the answers to the question, why is spatial in terms of data characteristics and analytics. Spatial data analysis has quite a few different issues, from data science. Alright, this is the end of the other lecture. Hopefully you enjoy it and you see you all in the next lecture. If you've not subscribed to my channel, kindly subscribe, comment, share, and like. Thank you very much. All the best.